Hello everybody, this is Dr. Thunder. Today, I would like to show you how to solve a US high school physics competition question. This is question number 14 of 2025 F equals MA exam. Question 14 is related to question 13. So we have a tennis ball launcher. It can fire a tennis ball along the floor at some initial speed v, and then without applying any rotation to the ball. So the ball initially slips along the floor, then start rotating, then start rolling without slipping. So initially the ball will slip, but at some moment it will roll without slipping. So in this question, the ball launcher will launch three kinds of ball. The first one is a tennis ball. The second is a solid wooden ball. And then the third one, I do not draw here, is a rubber ball, solid rubber ball. The mass of tennis ball is M1, the wooden ball is M2, and the rubber ball is M3. M1 is less than M2, M2 is less than M3. And for this tennis ball, we can treat it as a hollow sphere because tennis ball has a very thin shell of rubber, so most of the mass is on this on this shell of the tennis ball. So we want to find out which ball has the highest final velocity. So all three has the same initial velocity v, but we want to find out which ball or which balls will have the highest final velocity. Now let's begin with a tennis ball or M1. So during the ball slipping, we have a friction force F1. F1 is M1G, mu is friction coefficient. So then we apply the impulse momentum theorem. So F1, because F1 is along the left direction and the V is to the right direction, so we have a minus sign here. So F1 delta T, which is the force impulse, that's equal to the change of momentum. So then we have delta V1 equals to minus F1 over M1 delta T. Now this can give us an equation for V1, the speed of this tennis ball after its launch. So V1 equal to V minus F1 over M1T. This is equation 1. So then we will also look at the torque impulse versus the angular momentum theorem. So torque is F1R. R is the radius of the ball. So torque delta T equal to the angular momentum change. So then angular momentum is I1 omega 1. I is the moment of inertia. When we calculate the moment inertia, we use the moment inertia is relative to a rotating axis going through the center of this tennis ball. So delta omega 1 then equal to tau 1 over I1 delta T. Then we have this equation for omega 1 that is tau 1 over I1 by T. We know that torque tau is F1R. Then we have this equation 2. Then when V1 is equal to W1R, the tennis ball will roll without slipping. So and it also reach its final speed. We know this in the question 13. Please go back to look at my video for the question 13. So then we combine, we plug equation 1 and equation 2 into this equation. Then we get this. Then we solve for t. Then we have t here. Then we plug t back into equation 1. Then we get v1 equal to this, and we clean up. Then the only thing we don't know is I1. I1 is the moment inertia. Moment inertia is usually defined as the mass multiplied by the distance, square distance. The mass, the distance is from the mass to the rotating axis. So for a hollow ball like a tennis ball, then we have an expression for its moment inertia. We assume it's n1. M is the mass of the tennis ball. R is the radius. So in the tutorial later, I can show you by using integral method, we can calculate the moment inertia of a hollow ball, and it's 2/3 mr squared. So for the hollow ball, we have n1 here. So then we plug this into v1 expression. So eventually v1 is calculated to be v over 1 plus n1. So as we can see here, this v1, the final speed of the tennis ball, has nothing to do with the mass of tennis ball or the radius. It only has relation with the initial speed, and then also this coefficient n1 here. N1 is 2/3 for a hollow ball. So now for the solid ball, like 2, which is a wooden solid ball, and 3, which is a rubber solid ball, the expression for the moment inertia will be similar, but with a different coefficient. N2, we use N2 here. As I mentioned, in a future tutorial, I will use the integral method to calculate the moment of inertia for a solid ball. And then let me review the answer here. For a solid ball, the moment of inertia is 2/5 mr squared. Remember, all this moment inertia is relative to a rotating axis going through the center of the ball. So now we have different coefficient N2 here. So for a solid ball like ball 2 and ball 3, then the final speed v2 equal to v3. It's v over 1 plus n2. If you don't know the moment of inertia for hollow ball or for solid ball, it's okay. We can still figure out. We just compare the n1 and n2, or these two coefficients. Based on our common sense, for the ball with the same mass and radius, hollow ball will have larger moment inertia, because for the hollow ball, most or more mass is on the outside of the ball, or on the shell ball. But for the solid ball, the mass is evenly distributed all over the ball. So for the hollow ball, you will have a larger moment of inertia than a solid ball. So that means N1 is larger than N2, which is actually true here. See, N1 is 2/3 and N2 is 2/5. But we don't need to know these numbers here. We just need to know that based on common sense, that N1 is larger than N2. So because N1 is larger than N2, so from these two expressions, then V1 is smaller than V2. But we know that V2 is equal to V3. So ball 2 and ball 3 will have the highest final speed. So this is answer D. Thank you for viewing. If you think my tutorial is useful, please comment, like, and subscribe.